Let us discuss in this video the notion of limit. What is a limit? So a limit of a function, and we will write it limit of the function f of x as x approaches a is equal to the number L, capital L, okay, if and only if, or the idea behind this is going to be that the values of f, the values of f of x get arbitrarily close oops, to L as x gets, well, as x gets close to a, okay? But here it's important that it's not equal to a, okay? So the limit of f of x is equal to L as x approaches a if the values of f of x get as close as you could imagine to the number L as x gets close to a. Okay, that's the idea. So let's see some examples, some graphical examples to see what we are discussing here. So for example, if I would ask, let's say this is the point 2, 1, okay, here. And I have a function that does like this. And then I ask, what is the limit as x tends to 2 of f of x? What would you say? So if you notice here, let's go with this idea. The values of f of x get arbitrarily close to L. Okay, so the values of f of x are the points here in the function, in the graph of the function, right? So as x gets close to a, that means when x gets close, that means that we're traveling towards 2, right? In this case, a equals 2. So you see what's happening, right? Or you could go from the left. Okay, as you go towards 2, what's happening here? It looks like they are going to end up at this point, right? So what is the limit then? The limit when x tends to 2 of f of x is equal to 1, okay? So this is a function that has a missing point there, okay? It has it's not defined for x equals 2. But careful here, because let's say this is 2, and I define f of 2 to be equal to 2. So does anything change here? So let's look at the definition again. It says the values of f of x get arbitrarily close to L. Okay, so we travel on the graph. Okay. And then we end up here in this point, f of 2 equals 1. Okay, but notice that f of 2, by definition of the function, is 2. But here, what does it say? But not equal to a. So the value of f at the point a is completely irrelevant. Okay, so this is a warning we need to keep in mind. So the value of f of a, okay, is irrelevant to the limit of the function f of x as x tends to a. Okay, so basically we can redefine the value of the function at x equals a, not change the limit, by doing that, okay? Okay, so this is one possibility. Let's, but the function could be perfectly all right also, okay? So let's say now I draw the function f of x equals x, okay? And I want to find the limit of f of x when x tends to 4. So what's the limit in this case? So if we approach when x moves towards 4, okay, the values of f of x are moving towards this point here, right? And we can go from the left, also, sorry, from the right also. So they will be traveling this way. So it looks like the limit will be the value at 4, okay? Or actually, because we know it's equal to 4, so let's just write it down, okay? In this case, the function, we define it, it's continuous, right? We can trace the graph without lifting the pen from the paper. But again, I could decide, okay, well, let me redefine it here at x equal 4 and use a different point. The limit would be unchanged, okay? All right, so more things that could happen here. So let's say, for example, I take a function that is 1 over x, okay? 1 over x is going to look like this. So let's say I want to find the limit when x tends to 0 of f of x. So what is the limit in this case? So if we approach x equals 0, right? We approach from the left. The points seem to go all the way down, okay? There's an asymptote. If we approach x equals 0 from the right, it seems we keep going up and up and up, okay? And then there is a jump here, okay? It's broken. The graph of the function is broken. So what happens here? The limit does not exist, okay? Because they don't meet anywhere, okay? They don't approach each other, if you want. So this is what is called an asymptote. Okay, so this is another warning we need to keep in mind. Warning: limits do not always exist. Okay, so this is very important to keep in mind, because we will see examples, lots of examples that there will not be a limit. So it's important to know. Okay, it can be very dramatic like this, or it could be a little less dramatic. Let's say 1 over the absolute value of x. Okay, in this case, the negative part flips, okay, becomes positive. Remember the definition of absolute value. The absolute value changes the sign from negative to positive, and the positive stays as it is. Okay, so in this case, the limit as x tends to 0 also does not exist. You see what is happening? As we approach x equals 0, we keep going up, right? But there is no value that we are approaching from both sides, okay? Infinity is not a number, so if you were thinking the limit is equal to infinity, we will talk about this. But keep in mind that it's not a number, okay? We could also do something more innocent. Okay, just say, well, okay, maybe I have a function, let's say here x equals 1. Okay, and I have a function that comes like this from the right, and then somehow there is a jump, and the function does like this. Okay, let's say here we have -1, and here we have 1/2. So in this case, the limit when x tends to 1 also does not exist. Okay, you see why? Because as we approach from the left or we approach from the right, they don't come close to each other. Okay, so those are different possibilities that we will see happening. So in the next few videos, we are going to keep working on these ideas, the ideas when do limits exist, when they don't exist, approach from both sides, and then learning how to compute limits.